Hello fellow skeptics, I'm Luther Name, and this is the 17th video in a series addressing the broad topic of, is something wrong with modern physics? If so, what? And can it be fixed? Now, it's been a while since I made my last video. Partly it's because of the season of the year, but also partly because I wound up going down a rabbit hole with respect to looking at things I wanted to validate again. My modus operandi is to go back and review what I've said in the past videos, and then to play that against what I expect to say in the current video. There were things I wanted to double check. That led me to going back to Mathematica, which I have not used in several years, and it turns out that there's a learning curve. If you don't use it continuously, well, then you have to get back into the mode of using it and refamiliarizing yourself with the syntax and validating that the algorithms that you're developing, in this particular case they had to do with a special relativity in terms of the Doppler and aberration effects. I was trying to extend the analysis that I was familiar with into areas that I was not particularly familiar with, and that was a rabbit hole, and I finally decided I wasn't going to do that. We can just discuss what the aspects of it are. This will be the final video in the special relativity area. Again, as I had indicated before, the kinematic part of special relativity just doesn't exist. It's all a misinterpretation and misapplication of the electrodynamic part, where we're using electromagnetic radiation, flux of photons, to basically accelerate various types of mass to make measurements. And what we're doing is misinterpreting how that dynamic process works. So with that, what I'm going to do is I'm going to basically state what I feel are the final issues relating to the Doppler and aberration equations. I'll show a few diagrams in a few minutes, but this will not be nearly as extensive as in the past. In the past, I've said with regard to the Doppler and aberration, one of the things had to do with the characterization of the way Einstein described how he developed the Doppler and aberration equations. And it turns out that that's fundamentally one of the issues. The way he said he developed it is not really the way we use it. It's because he never really put himself in the position of actually making a physical measurement. When I said before that you needed to make a measurement, and of course if you're traveling in a particular direction and you're passing through a flux radiation that has its own vector, propagation vector, in order to detect something, well, you have to be looking at the source of radiation. Well, that's not entirely true if what you're looking at is the radiation pressure and the forces associated with the interaction of the flux with an object that's moving in space through a particular flux. It turns out to be irrelevant whether you're looking at the object or not. It's important in terms of the physics of whether or not the sensor system, as you're describing it, is properly accounting for how the flux interacts with that sensor. Take a radar, for example. You typically don't shine radiation on the back of a radar or a radiometer of some sort. What you do is you basically are looking in a particular direction at radiation that you'll intercept. Turns out that that's still true, and it's important if you're trying to get an integrated picture of how the flux is impacting that particular object. But it turns out that it's irrelevant in terms of whether the Doppler aberration effects are properly calculated. Einstein's equations, as he put them together, in fact work very well that way, and you have to be careful when you set up a scenario that you're using the proper equations. Einstein's equations very well describe what the aberration effects and the Doppler effects, or the frequency shifts associated with the motion of an object through the flux may be. So anything that that you may do in order to fully describe the scenario and the actual process of making a measurement, that's separate from the actual Doppler and aberration effects that occur at the object. The radiation must interact with the object, and when the radiation is interacting with an object, you can detect in one way or another that radiation exists. It must include the aberration effect and the whole object. If the radiation, for instance, were incident on the back of a radiometer looking in a particular direction, the same effects occur regardless of whether you're looking at the flux or whether you're looking away from the flux. What you're measuring, though, depends on whether or not you're moving in a particular direction relative to the flux propagation direction. So, and I'll reemphasize this in the visuals. The main issue is that Einstein developed his two famous equations for the Doppler and aberration effects, but he used them separately. And he did not really look at the fact that when you're making a measurement, you are actually interacting with the flux in the object, and what you see then is not just the unaberrated radiation. All you see is the aberrated radiation. You must include the aberration in the Doppler expression where it's incorrect. This is exactly the same kind of issue as arose if you go back to Newton's equation for gravity. He used the point mass model, and we got results that were okay. That worked very well, with the exception of those things of academic interest. The same thing is true the way we use his Doppler expression. It's good enough for practical purposes. In fact, because the motion of most man-made objects, most celestial objects, are slow compared to the speed of light. Therefore, what we call beta, which is the ratio of the velocity divided by the speed of light, is like 10 to the minus 3, 10 to the minus 4. Even the Earth circling the Sun at 30 kilometers per second is moving with a beta of 10 to the minus 4. So we can make small angle approximations, and we get results that are very good. We can't really effectively measure the small Doppler shifts associated with these small betas, and so we make approximations. But for academic work, especially if we're talking about particle accelerators where we are moving objects at very high values of beta, these approximations don't hold. What I was doing when I began to work with mathematics was begin to look more carefully at the large beta effects of the, excuse me, especially of the aberration effect itself. So I decided not to go any further with that other than a brief description of some things that you can expect that are totally out of the ordinary in terms of what we're familiar with. But his Doppler and aberration equations are correct as far as they go and for all practical purposes. But there are other things of academic importance where you have to be much more careful about the equation you use. You can't use his expression for the Doppler as is. You must use the correct expression that shows the aberration effect associated with the interaction of the radiation with the material in some fashion to give a measurable effect, whether it be an electrical effect, whether it be a radiation pressure effect, a dynamic effect associated with that. So with that, let's take a look at the visual of the equations that Einstein developed and how you must use them. We've been using them incorrectly, but we haven't known we've been using them incorrectly because we basically can't measure the effect of the aberration very well. There are a few cases, and I pointed out in the last video, that there is possibly an effect that's been observed with observing the sun and the solar radiation, that in fact, if you use the aberration correctly, then you can begin to describe some of the idiosyncratic responses or the effects that we're seeing. In terms of measuring frequencies, it's very difficult to measure these very small frequencies with a Doppler, with optical radiation. But we can measure some of these effects with radars and microwave systems that are extremely sensitive. They in fact do measure things in the frequency domain as opposed to optical systems, which tend to measure in the wavelength or spatial domain. So there are some things that we could address in terms of microwave radiation and observations that we make, because we can begin to see some of the very small frequency shifts associated with motions that now are in the small beta domain. And that's about the only way we can measure them. So with that, let's go to the visuals and bring this discussion to a close. What we're going to do in this series of slides is discuss Einstein's equations from his 1905 paper and how they need to be modified to deal with the various scenarios, measurement scenarios that we're going to be looking at and investigating, or at least showing how to set up. As you can see here, the key point is the Doppler is given in terms of the cosine of the angle phi, which is the uninteracted direction of propagation of the radiation with respect to the motion of an object. However, his aberration is given in terms of cosine phi prime. This is what we measure. If we make a measurement or any interaction of the radiation with a sensor or object, it's phi prime. And so what we have to do is adopt phi prime, cosine phi, and include the effects of the aberration phi prime, and become geometry dependent. And that's exactly what we're going to be discussing. The prior discussions led to this point, which is to address how we would address various scenarios. The radar scenario was pretty self-explanatory. We're looking at, as we've talked before, about the radiation pressure. You have a flux incident on a surface. It can be a large surface, it could be just an incremental surface element. And we need to be able to describe what's happening with respect to the aberration in order to be able to tell what's happening. And so in this case, we have an incident flux. The object is moving through it. We would have the normal geometric reflection or absorption if there were no aberration, and that would be if the object is not moving with any particular speed through the flux. Or if it's moving, then there will be an aberration. And that aberration is given by a small delta, which is the difference between the aberrated angle and the, in this case, the incident angle. So as we showed in the prior example where we have an incident angle on a surface given by psi, this is what we finally wind up with as a statement of the frequency with respect to that particular scenario and that geometry. And this is what the equation looks like with respect to the angle psi incident on a surface area. And psi prime given by delta, and delta can be shown using various small angle and small beta approximations to be given by these kinds of simple expressions. These are just a repeat of the various expressions and the angles that are involved and how you modify Einstein's equations to accommodate these other angles that we might find useful in various scenarios. And in the next slide, I'll show one such scenario. So one We talked about this kind of scenario before with respect to radiation pressure. You've got an object, say it's in orbit, radiation flux is incident on this cylindrical object moving with some orbital velocity through the radiation flux. And if it's also rotating, why then each incremental area on the surface would have a different, would have a particular velocity component relative to the flux. And so the radiation pressure would be different at each of these points. And so we would use these geometries. If we were lucky enough to have something that was nice and analytical and cylindrical like this, then we could just integrate and find out what the total flux is. And of course, then recoil forces associated with those act to slow this lateral velocity through the flux and to slow the rotation rate of the object itself. These are idealized, but and also this angle and this angle are not the same, even though they're labeled the same. I just want to make an additional point about these kinds of objects that may be moving laterally through some radiation flux. We've learned a lot over the last 50 years in terms of how to deal with arbitrarily shaped objects, radar scattering, learning how to calculate the integrated effects across arbitrary shapes. Radar cross sections were one of the first things that were looked at. In terms of stealth technology, you also have faceted surfaces, arbitrary surfaces. We know how to deal with these kinds of things. So while it's all nice and easy from an academic perspective to look at regularly shaped objects that can be analytically described like cylinders and rotation, it's not necessary. We have more than enough expertise and computational power to be able to deal with objects of arbitrary shape. If this should prove to be necessary, as we've stated before, from a practical perspective, the effects we're looking at tend to be very small. So the amount of detail that needs to be applied to these kinds of shapes and scenarios is problematical. Let's take a look at another idealized geometry and carry the analysis a little bit further. Let's say we have a rectangular cross-section object with radiation coming in at some angle, psi, in one end, and makes multiple bounces and exits. Because the object is not moving relative to the direction of the flux, why the entrance angle and the exit angles are the same. Now, where we might run into this would be internal elements in a telescope and some sensor configuration, or possibly a microwave device where we've got a waveguide and the radiation is propagating along and back and forth, possibly resonating. We're not going to carry the analysis that far, but there are possibilities that this geometry could in fact arise, and we have to be aware of it. So here we put the object in motion. So what we have then is the aberration causes the first reflection to have a deviation, and that accumulates until the ray exits, and now it no longer exits with the same angle as it entered the parallel plane system, and it has a new output angle. So what you can see here is that if you've got multiple reflections, what you do is you accumulate the deviation, the aberration angle itself. In this particular level of approximation, why you have n reflections, you have n times the single deviation in the angle that occurs. What this causes, if you have an eidolon like in a laser or a microwave resonator tube, you potentially have a difference in the path length, which changes the resonant conditions then of the radiation within that particular cavity. This slide is just kind of a review of things we've said before. This is the general expression given this particular type of geometry for what the frequency change might be on the radiation that's either absorbed or reflected from an object that's moving laterally with a beta through some flux. And using a small beta approximation, We can find very easily that this is the same result as we found before for the Doppler shift. And at 90 degrees, again, we have results that are consistent with what we found from other techniques. However, given the issue associated with making sure that for all angles that you're looking at in the small beta approximation that you're using the correct form for the frequency change, if you're going to go to the trouble of making these calculations, you're going to be making numerical calculations rather than analytical. And as a result, it's just as easy to use the complete expression for all the angles psi, as we discussed previously, that may represent a variety of incident angles across an arbitrary object. And so you can just use the complete expression. It's much safer that way. Roger Penrose, Nobel laureate from England, apparently at one point did look at the effect of the aberration, but I don't know. It was pre-computer days. I have no idea what he actually saw, but we see various interpretations of what the Doppler ought to be as the velocity of beta increases very high. Science fiction shows these things. You see a number of artistic representations. Star Wars had the leap to hyperspace showing particular characteristics. Those stars are all black and white. There is no color change, which is not quite correct. Same thing with the program Stargate. Again, there was no color change, no frequency shift as such. It was an angle shift, but they didn't really account for the frequency. And it turns out to be more complex than just looking at the aberration angle itself. And so rather than continue it on, keeping with the basic theme of this presentation, these are the kinds of things you need to do and the kinds of equations you need to use. Now it's up to somebody and I may do this as a matter of fact, given the paucity of information that we really have on what the Doppler shift would be as a function of beta, I'm going to explore that in another video that's not part of this particular series. What I've done here with this series of slides is I've explained how to do it, and in limited case for the aberration, what to do and how it works out. Not so much for the frequency shift, and we'll look into that in this other presentation. In this particular instance, what we're going to do is move on from the special relativity into general relativity. So as you can see, the prior slides, there were a lot of them. I put them in and ran through them pretty quickly because I wanted them to be there as reference for anyone who wants to dig into this. Again, the original scope and the one I tried to adhere to is to show how to use these equations, the proper way to use them, things that had been missed or omitted. The goal wasn't really to do all the work. There's time for that. I will have a series of videos after I'm finished with this series on modern physics to just discuss some elements of the science and technology, including the Doppler shift itself, to try and supply some clarity to what the artistic representations ought to be, and also to address other anomalies, things that have kind of troubled me a little bit in terms of what we think we're talking about in terms of the applications of some of these scientific elements and to various technologies and the kind of technologies we might be looking at. Simple things like communicating with a space vehicle that may be moving at a large fraction of the speed of light. How would we do that? Why would we do it? What would be the consequences? And this all was part and parcel of how do you measure things? What are you looking at? What are you seeing? How do you interpret what you're measuring? So I'm going to get into that a little bit more, but not here, and not in this sequence of videos. Next one will be, as I mentioned, on general relativity. So with that, again, thank you for watching. Subscribe, leave a comment, and I'll see you in the next video.